So remember way back to the first week of the semester, we began our discussion of electrostatics by introducing Coulomb's law to calculate electric fields. Coulomb's law was rather cumbersome, but could be used to find the electric field of any charge distribution. But after that, we investigated this idea that if the charge distribution contained sufficient symmetry, that is, if the charge distribution was a highly symmetric one, we could calculate electric fields in a much more elegant fashion using Gauss's law. Now fast forward to the topic of magnetism. We began our discussion of magnetism by introducing the Biot-Savart law to calculate magnetic fields. Like Coulomb's law, the Biot-Savart law can be used to find the magnetic field surrounding any current distribution, with the aid of computers perhaps. So now a rhetorical question. Isn't there a Gauss's law equivalent for the Biot-Savart law that could allow us to calculate magnetic fields with ease and elegance? And the answer is yes. Just as we could apply Gauss's law for cases where charge distributions contain sufficient symmetry, we can apply Ampere's law for cases where current distributions contain sufficient symmetry. So, when can we apply Ampere's law in calculating magnetic fields surrounding current distributions? Two criteria must be met. First of all, Ampere's law only applies to the case of steady-state currents, that is, when current distributions are constant in time. Secondly, the current distribution must be a highly symmetric one in order for the application of Ampere's law to be helpful in evaluating magnetic fields, as the following examples will illustrate. So before we get ahead of ourselves, we'd better address the very fundamental question, what is Ampere's law? Rather than simply stating Ampere's law, we can derive it from a previous calculation we made using the Biot-Savart law. You recall in the last lecture that we calculated the form of the magnetic field at an arbitrary point outside of a current-carrying wire with a circular cross-section. So here we have the cross-section of the current-carrying wire. The blue dot in the middle shows us the current in the wire is coming out of the page towards us. Here is an arbitrary point P outside of the wire, a distance R from the center of the wire. And you recall that the Biot-Savart law we used in the last lecture to give us both the magnitude and direction of the magnetic field at that arbitrary point P. We saw that the magnitude of the magnetic field was given by this universal constant mu naught times the current divided by this factor 2 pi r. And when we use the right-hand current rule, this tells us that the direction of the magnetic field. In this drawing, placing the thumb of your right hand in the direction of the current and letting your fingers curl in the direction of the field, we see that the field points in a counterclockwise direction and that it must be tangent to the circle at every point. Now, Ampere's law gives us a relationship between the line integral of the magnetic field evaluated around any closed integration path. So it's the relationship between the line integral and the steady-state current in the wire. Since the current distribution takes the shape of the cylindrical wire, it is convenient to choose a circular integration path, sometimes referred to as an Amperian loop, since the magnetic field will be constant at any point along the path of fixed radius. Now here's a case where the symmetry of the current distribution tells us something about the magnetic field. Since there is no angular dependence to the current distribution, we would expect the field would have no angular dependence either. In other words, at a fixed radius from the wire, okay, the magnitude of the field should be the same value. So we start by evaluating this line integral using the value of the magnetic field that we already determined using the Biot-Savart law. Remember that in the line integral expression, ds represents the infinitesimal displacement vector along this closed integration path. Okay, so in our case, we see that the magnetic field is parallel to ds, that infinitesimal displacement vector, at each point along this integration path. The integration path here is shown as a dotted line here. So the magnetic field vectors I've displayed in green, and let me show you a few of these displacement vectors ds. So we note that ds is always parallel to b at each point. Okay, therefore, when we take the dot product of the field and that displacement vector, we find out that the argument is 0. So, okay, we're taking the cosine of 0. And when we substitute the value for the magnitude of the field that we already determined using the Biot-Savart law, that is the mu naught I over 2 pi r, we can substitute it in there since we've figured out the magnitude of this field in a different way, okay, without relying on Ampere's law. Note that the magnitude of the magnetic field is constant at each point along the circular path. This will allow us to take that expression for the magnetic field outside of the integral, since it is a constant at each point along the path. So when we look at evaluating that line integral around the closed Amperian loop, okay, b dot ds, okay, the expression mu naught over 2 pi r is a constant for that entire integration path, and therefore can be taken outside of the integral. So what we're left with then is simply the integral of ds around a closed loop. And when we sum up all of those infinitesimal displacements around the integration path, we simply get the total length of that integration path, which for a circle is just 2 pi times the radius. So when we do the number crunching, we do the algebra here, we find out that the 2 pi r factor in the denominator will exactly cancel that factor in the numerator. So the end result is that the line integral, okay, b dot ds taken around that closed integration path, in our case a circle, has this particular value of mu naught times I, okay, where I is that current that is encircled by our integration path. So it's important to note that we evaluated the line integral around a closed circular path, but the value of the line integral is the same for any closed path we could choose. It's just that the circular path made the integral particularly easy to evaluate. So now we can formally state Ampere's law as follows. The line integral b dot ds evaluated around any closed integration path is equal to this permeability constant mu naught times the current enclosed by the path. And we'll reiterate some of the following points already made about Ampere's law. First of all, the line integral is taken around any closed path, and we'll talk more about what sort of path we're going to be looking for our current distributions. And secondly, the current on the right-hand side of Ampere's law is the total current passing through any surface that is bounded by the closed path. So, as we said in the introduction, Ampere's law is to magnetic fields what Gauss's law is to electric fields. that it allows for a much simpler calculation of the magnetic field when sufficient symmetry exists in the current distribution, in the same way that Gauss's law allowed for a much simpler calculation of the electric field when sufficient symmetry existed in the charge distribution. So let's take a closer look at this comparison, because while there are many similarities between the two laws, there are also important differences that you want to be aware of so you don't get them confused with one another. So starting with a statement of each law, okay, here's Gauss's law as we formally stated it in a prior chapter, and we will just restate Ampere's law. We notice that in Gauss's law, the integral we're talking about is a surface integral, whereas in Ampere's law, we're talking about a line integral. When we apply Gauss's law, we are evaluating that surface integral over a three-dimensional closed, what we call Gaussian surface, a three-dimensional closed surface. Whereas when we apply Ampere's law, we're evaluating the integral over a two-dimensional closed Amperian loop. In Gauss's law, we choose a surface such that the magnitude of the electric field is either constant or at least piecewise constant over the surface. And you might expect that when we apply Ampere's law, we want to choose an Amperian loop or a two-dimensional integration path such that the magnetic field is either constant or at least piecewise constant over the loop. On the right-hand side of Gauss's law, we see this proportionality constant, 1 over epsilon naught. So we see that the surface integral is related to this universal constant, the permittivity of free space, whereas in Ampere's law we see that the line integral is related to this permeability constant, mu naught. In Gauss's law, the quantity enclosed by the surface is the net charge, whereas when we apply Ampere's law, the quantity enclosed by the surface is the net or total current. And finally, the resulting field that we get by applying Gauss's law, remember, is the net field due to all the charge in the problem, not just the charge that's enclosed by the surface. We can say the same when we apply Ampere's law, that the magnetic field that we obtain is really the net field due to all currents, not simply the ones enclosed by our Amperian loop. So let's take a look at a rather simple problem that will give us some practice in applying Ampere's law. In upcoming examples, we will be interested in using Ampere's law to determine the magnitude of the magnetic field at various points in space. But the purpose of this example is simply to gain some practice in seeing what the law means and in applying the line integral. So in this example, we are given the form of the magnetic field, and we're simply going to use Ampere's law to evaluate the line integral. So the Amperian loop, that is the integration path, has been chosen for us. It's the gray rectangle shown in the figure. And you can see that the field is not a uniform field, but rather increases in strength as you move up vertically. Remember that according to the field line model, as the field lines become more concentrated, the field becomes stronger in that region in space. Now we can break up our Amperian loop into 4 segments. We'll call them AB, BC, CD, and DA. Note that the sum of these 4 segments constitutes a closed loop, a requirement in applying Ampere's law. We will arbitrarily choose to traverse the loop in a clockwise direction when evaluating the line integral, although this choice is purely arbitrary. We could have chosen the counterclockwise direction if we so desired. So starting at point A, The first segment of our loop is AB. So we need to evaluate the line integral over this piece of the closed path. Note that the magnetic field B and displacement vector ds are parallel to one another, making the cosine of the angle between them 0. Also note that B is constant over the entire portion of the path, which allows us to take it outside of the integral. Thus, the integral of ds over the path AB is simply the length of the path L. Multiplying by B sub AB, we get our expression for the line integral. For the next segment, BC, we note that the magnetic field is perpendicular to ds. And since the cosine of 90 degrees is 0, the line integral has a value of 0 as well. For segment CD, the magnetic field and the infinitesimal displacement vector ds are antiparallel, making the argument of the cosine function 180 degrees. Once again, B is constant over this path and can be taken outside of the integral. The line integral takes the value minus B sub CD times L for this portion of the closed loop. And for segment DA, the magnetic field is once again perpendicular to ds for the entire path, giving us a 0 value for the line integral. So we now need to add up the values of the line integral for each of the 4 segments to get the expression for the line integral over the entire closed path. When we do this, this gives us the difference between the magnetic field at the top of the loop and bottom of the loop multiplied by the path length. That's the value of this line integral taken over the entire closed path. Although we don't know the exact value of the magnetic field at the top or bottom of the loop, we can reason that since the value of B is bigger at the top than the bottom, the line integral has a non-zero value. If the left-hand side of Ampere's law is non-zero, then the right-hand side must also be non-zero, which tells us that a current must exist in the interior of the loop. So now that we've formally stated Ampere's law and we've gained some practice evaluating the line integral, let's describe a general approach or strategy that we can use in applying Ampere's law to determine the magnetic field for a current distribution. Remember that the purpose of Ampere's law is to help us find the magnitude of an unknown magnetic field surrounding a current distribution. So the 7-step strategy outlined in this slide can be used to find the form of the unknown field in the problems that follow. So the first step is to identify the symmetry of the current distribution and the pattern of the magnetic field lines. Remember that magnetic field lines always encircle their sources. Next, we need to choose an Amperian loop, that is an integration path, that matches the symmetry of the current distribution so that the magnetic field has a constant magnitude along the entire path, or is at least constant over various segments of the path where the line integral is not equal to 0. Now you recall in the last example we looked at, we saw that by choosing that rectangular Amperian loop, the magnetic field was constant in magnitude over each segment of the loop, or it was perpendicular to the infinitesimal displacement vector ds such that the value of the line integral was 0 for those portions of the path where the magnetic field was not constant. Next, we draw an appropriate Amperian loop so that it passes through the field point where we're trying to find the magnetic field. We use the symmetry of the current distribution to determine the direction of the magnetic field along the integration path. As we said previously, with a smart choice of path, the magnetic field will be either parallel or perpendicular to the path, or perhaps anti-parallel. We use the right-hand current rule to determine the direction of the magnetic field lines. Next, we set up and evaluate the expression for the line integral. After doing so, remember the right-hand side of Ampere's law requires that we calculate the total or net current that passes through any surface bounded by the Amperian loop. Be careful with signs. If a problem involves a solid conductor and the integration path doesn't enclose the full current, calculate the enclosed current using the current density, where the current is equal to the current density times the area. And finally, we equate the line integral, that is the left-hand side of Ampere's law, with the encircled current, the right-hand side of Ampere's law, and of course multiply by that proportionality constant mu naught. And once doing so, we can then solve for B. So we'll start by applying Ampere's law to a problem we solved previously using the Biot-Savart law. Hopefully you'll see how much easier it is to apply Ampere's law than the Biot-Savart law. This is the problem of finding the magnetic field outside of a long straight wire with circular cross-section of radius big R. So here we have a right circular cylindrical wire. Okay, drawing it in 2 dimensions, we see it coming out of the plane, or at least here the current is coming out of the page towards us. So the first step is to identify the symmetry of the current distribution and pattern of magnetic field lines. Remember that magnetic field lines always encircle their sources. So for this current distribution, one with cylindrical symmetry, okay, this requires that the field lines form concentric circles about the wire such that the magnetic field has no angular dependence. So in green here, I'm showing you some of these magnetic field lines. The next step is to choose an Amperian loop, that is integration path, to match the symmetry of the current distribution so that the magnetic field has a constant magnitude along the entire path, or at least constant magnitude over various segments of the path. So you can see here that by choosing a circular Amperian loop, this allows the magnetic field to have a constant magnitude over the entire path. Once again, since there should be no angular dependence to the field. So we're going to draw our appropriate Amperian loop so that it passes through the field point in question. So we're asked to find the field outside of the wire. So we will draw an arbitrary circular Amperian loop, okay, which is shown in red here in the slide, okay, at some arbitrary point outside of the wire. Alright, so the next step is to use the symmetry of the current distribution to determine the direction of the magnetic field along the integration path. Okay, and in general we say that a smart choice of path, okay, will always make the magnetic field be parallel, anti-parallel, or perpendicular to the path, and we can see here that that is indeed the case, and we use the right-hand current rule to determine the direction of the magnetic field along our path. So here we see that using the right-hand current rule, that is, the current is coming out of the plane of the paper towards us, so we place the thumb of our right hand in the direction of the current, our fingers then curl in the direction of the field, which is in a counterclockwise direction. So it would make sense to traverse the loop in a counterclockwise direction. Okay, we note that the magnetic field is parallel to the displacement vector ds at each point along the integration path, and I'll show you some of these values here. So at this point along the integration path, B is tangent to the path, as is ds. Okay, here we can say the same thing. Both B and ds are always tangent to the path and parallel to each other. So we set up and evaluate the expression for the line integral. That is b dot ds evaluated around the entire closed path. Okay, and we note here that since b and ds are always parallel to each other, then the argument of the cosine function is 0. And since b is constant along that entire path of fixed radius, okay, we can take it outside of the integral, okay, which tells us that the integral, we are simply summing up all of those infinitesimal displacements, which gives us nothing more than the entire length of the path, the circumference of the circle, 2 pi r. So the next step is to determine the total current passing through any surface bounded by the Amperian loop. So in this case, the obvious choice of the surface would be a two-dimensional circular surface that is bounded by the circular path. And when we look at that surface, we see that the total current passing through the surface is simply I. So finally, we're ready to apply Ampere's law. That is to equate the left-hand side, or line integral, with the encircled current on the right-hand side. And the line integral has this value of b times 2 pi r. The right-hand side, okay, is equal to mu naught times that encircled current. Okay, we can now solve for the magnetic field, and we get this result that the field has a value of mu naught I over 2 pi r, which is exactly what we determined previously using the Biot-Savart law. So now let's apply Ampere's law to find the form of the magnetic field inside of a long straight wire of circular cross-section. So here we have the long straight right circular cylindrical wire. We're showing you a two-dimensional view of it. Okay. The radius of that cross-section is big R. The current is coming out of the page in the diagram. So once again, we start the problem by identifying the symmetry of the current distribution. Remember that magnetic field lines always encircle their sources. So in this case, the cylindrical symmetry of the current distribution requires that the field lines form concentric circles both inside and outside the wire in order for the magnetic field to have no angular dependence. So here in green, I'm showing you some of these field lines inside of the wire. So in choosing the Amperian loop to match the symmetry of the current distribution, okay, the obvious choice would be a circular Amperian loop so that B, the magnetic field, would be constant in magnitude over the entire path. We will draw the Amperian loop at an arbitrary point inside of the wire where we want to evaluate the magnetic field. So in this case, we'll draw a circular Amperian loop of radius little r, which is inside of the wire. Now that we've drawn our circular Amperian loop inside of the wire, we're now in a position to use the symmetry of the current distribution to determine the direction of the magnetic field along that integration path. So just as in the last example, we see that for current coming out of the plane of the page, using the right-hand current rule, the magnetic field lines point in a counterclockwise direction. Thus, when we evaluate the line integral, it would make sense to traverse the loop in a counterclockwise direction. Now, just like in the last example, we know that the direction of the magnetic field and the direction of that infinitesimal displacement vector ds are the same. In other words, they're parallel to each other and tangent to the integration path at every point in question. So here I'm showing you in the diagram, okay, for about 4 points, the direction of the field and the direction of ds. So we're now ready to set up and evaluate the line integral around this closed integration path. And the evaluation of this line integral is going to be identical to what we saw in the previous problem, right? The symmetry is exactly the same. We see that since b and ds are in the same direction, the argument of the cosine is 0. Okay, we also see that for our circular Amperian loop of fixed radius, the magnetic field is constant in value everywhere along that integration path, which means that we can take it outside of the integral, in which case we are simply left adding up these displacement vectors ds, okay, summing them up around the entire closed loop, which, as we saw previously, simply gives us the circumference of that circular Amperian loop, okay, having a value of 2 pi r. So our expression for the line integral is identical to what we saw in the previous problem. Now, when it comes to the next step, this is where things get different, because in this problem, when we look at the current that is traversing a two-dimensional circular surface bounded by this Amperian loop, we see that not all of the current in the wire passes through that surface. Only a fraction of the current passes through the surface. And this is where we need to use the concept of current density to be able to calculate only the amount of current that is encircled by our Amperian loop. So we get that encircled current by multiplying the current density, which remember is a current per area, times the cross-sectional area of that Amperian loop. So the current density, okay, is the current divided by pi big R squared. Okay, that is, big R is the radius of the entire wire, right? So that gives us a measure of, okay, the current density. But now we're going to multiply by simply the area of the two-dimensional circular surface bounded by the loop, which is pi little r squared. Okay, so when we do that, we end up with the expression you see here on the screen. Okay, and finally, our last step, we can apply Ampere's law, equate the line integral on the left with the encircled current on the right. Okay, and when we do this, we end up with a fact, okay, the magnetic field takes on the following form. So let's summarize our findings from the last two problems. That is, the form of the magnetic field both inside of and outside of a long, straight cylindrical wire. So we'll use the symbol big R to represent the radius of the wire itself, where we'll use the symbol little r to represent the distance that the field point is from the center of the wire. So starting with the form of the field inside the wire, that is for little r less than big R, okay, we see this result from our last problem. Now when we look at the form of the field, okay, we notice that the magnitude of the field increases linearly with distance. Right? The magnitude of the field has a linear relationship with the distance that the field point is from the center when we're inside of the wire itself. So if we were to graph this relationship, that is field as a function of distance, we see that while for all points inside of the wire, okay, the field increases linearly in strength, okay, linearly with distance. Once we get to the wire boundary, however, and now we're looking at field points outside of the wire, we see now that there is this inverse relationship between field strength and field distance. So this is our typical inverse relationship here. Do you see how this result exactly parallels the form of the electric field for a uniformly charged insulator having spherical symmetry? Okay, that the field increases linearly with distance from the center while inside of the charged insulator, but that it decreases inversely with distance once outside of the charge distribution. This is a result we saw previously when we applied Gauss's law to the case of electric fields. So let's now take a look at the form of the magnetic field for a very important current distribution, that of the solenoid. Solenoids are used everywhere in modern technology to produce magnetic fields. So an understanding of the form of the field both inside and outside of the solenoid becomes of particular importance. Shortly, we'll investigate some practical uses of solenoids in technology, but first, let's take a look at the magnetic fields they produce. Remember that a solenoid is nothing more than a coil of wire with a given length. The turns of wire can overlap each other as well as exist adjacent to each other. The most common geometry for the solenoid is to have circular turns of wire. It's important that we distinguish between the field region inside of the solenoid and outside of the solenoid because, as we'll soon see, it's the difference in field strength between these two regions that make the solenoid so useful in technology. So as always, we'll start by identifying the symmetry of the current distribution so that we can determine the pattern of the magnetic field lines. Now, to determine the magnetic field line pattern, we're going to consider two loops of a loosely wound solenoid. So here we have, you see the solenoid in the top picture of your screen. Okay, here we have one coil, okay, and this one loop of wire is perpendicular to the plane of the paper, and you see here that the wire coming out of the top, the current is directed out of the plane of the paper, whereas, okay, when the current goes back into the plane of the paper, as it for the bottom portion of this loop. Here we have an adjacent loop, and we've exaggerated the spacing between the loops so that we can examine the field in this region. So let's start by taking a look at the field in the region between these two loops. So we notice that using the right-hand current rule, you see the magnetic field lines, okay, for both the upper wires and the lower section of wire. The field lines are represented by these black arrows. So we see here that the left-hand upper coil gives us a magnetic field pointing upwards, whereas the right-hand upper coil gives us a magnetic field pointing downwards, which produces complete cancellation of these magnetic fields. So we have no net field in the region between, okay, these upper wires. The same can be said for the lower portions of the loop. Okay, magnetic field on the right points up, magnetic field from the wire on the left points down. So once again, we get complete cancellation. Let's now take a look at the region which will be in the middle of the solenoid between these wires. Notice that for the wire on the left, okay, the upper wire gives us a magnetic field pointing to the right, okay, whereas the bottom portion of that loop also gives us a magnetic field pointing in the same direction, that is right. The same can be said for our loop on the right. We see that the upper portion of that loop gives us a magnetic field pointing right. Okay, the lower portion of the loop gives us a magnetic field pointing right. Now you can imagine that for not just these two loops, but for the end loops, okay, the magnetic field in the interior of the solenoid is always pointing in the same direction. This gives us a very strong magnetic field in the interior of the loop. This is what we call the strong field region. When we now turn our attention to the region outside of the solenoid, okay, we see something sort of interesting happen here. Okay, you'll notice that, okay, when we look at the upper portion of the left-hand loop, the magnetic field points left. Okay, but we also need to look at the contribution of the field from the lower portion of this loop here. Okay, now since it is further away, it's going to produce a weaker field in this region. Okay, but the field now, okay, well, I'm showing you the wrong portion of the loop here. We also have, okay, this, the right-hand loop, okay, the upper portion gives us a field pointing in this direction. Okay, but as I was saying, when we look at the lower portion of the left-hand loop, okay, it produces a weaker magnetic field in this region, which is opposite, okay, the direction of the field from the top wire. Okay, it's weaker because it's further away. Okay, and the same can be said for the right-hand coil. Okay, when we look at the lower portion of that loop, okay, it produces a magnetic field in the opposite direction, okay, from the top portion of the loop, and it's weaker because it's further away. The end result is that we get partial cancellation of these fields, okay, from the upper loops and lower portions of the loops, okay, producing a weak field region. When we look at the field region below these loops, we see the same thing happen. Okay, so here we have the near field region, okay, due to the lower loops, okay, producing a fairly strong magnetic field. Okay, but when we add in the contribution of the magnetic field from the upper portions of the upper portions of the loop, okay, the near field regions, we notice that the fields are in the opposite direction. So once again, we get partial cancellation of the fields, okay, producing a weak magnetic field outside of the solenoid. So when we look at what we call the long solenoid limit, that is when the length of the solenoid is much, much greater than the diameter of the solenoid, okay, we see two things. First of all, the magnetic field becomes both uniform and very strong in the interior of the solenoid. Okay, so we see here that these magnetic field lines, okay, are very, evenly spaced, okay, showing a very uniform field here, okay, and a very strong field as well. Okay, when we look at the field in the region outside of the solenoid, in that long solenoid limit, okay, the field becomes extremely weak, okay, and it approaches zero. It's interesting to note that the magnetic field of a solenoid really resembles that of a bar magnet. When we actually look at, okay, the magnetic field lines, that magnetic field configuration, it is very, very similar to that of a bar magnet. So now that we know what the magnetic field looks like, both inside of the solenoid and outside of the solenoid in the long solenoid limit, we're now ready to choose an Amperian loop so that we can evaluate the line integral. So as always, we want to choose a loop so that the magnetic field will be constant in magnitude over each portion of that loop. So here we see the form of the magnetic field, both inside the solenoid and outside of the solenoid. And you'll notice that if we were to choose a rectangular Amperian loop, that the magnetic field will be piecewise constant over the entire loop, okay, when the long solenoid limit is observed. Remember that the magnetic field is uniform inside of the solenoid and has a value of 0 outside of the solenoid. So we're going to draw a rectangular Amperian loop of length L and width W, which passes through an arbitrary field point in the interior of the solenoid. That's where we're trying to find, okay, the value of the magnetic field. So here you see our red integration path, our red Amperian loop. So we need to determine what the magnetic field looks like along each portion of that integration path. And we see that since the field is uniform inside of the solenoid, okay, the value of the magnetic field, these green arrows I'm showing you on the slide, okay, which has a constant magnitude, okay, whereas for all portions of that loop that exist outside of the solenoid, okay, the value of the field is 0 there. So when we evaluate the line integral, we're going to start from the lower left-hand portion of the loop, and we're going to traverse it in a counterclockwise direction. All right, so we are now ready to evaluate the expression for the line integral, okay, around this closed Amperian loop, which we've sort of divided up into 4 pieces. So you see here, I'm showing you in red the little infinitesimal displacement vector ds for each portion of the loop, okay? And starting with the bottom portion of the loop, when we evaluate the line integral, we notice that the field is uniform for that entire portion of the loop. It has a constant value. We notice that it is in the same direction as ds, so the argument for a cosine function is 0. So the line integral takes on the very simple form of b times, okay, the side length L. Now for the sides of the loop, we notice that the magnetic field is either constant or 0 in value, okay, but either way the line integral will have a value of 0. Okay, for the portion of the loop, let's say here, okay, where there is a field, okay, we notice that, okay, the field is perpendicular to ds, which gives us a 0 value for the line integral. Okay, for the portion of the loop that exists outside of the solenoid, we know that the value of the field is 0 there, so that gives us a 0 value for the integral for a completely different reason. Okay, but the bottom line is that, okay, for the loop, both loop sides, that is the left-hand side and the right-hand side, okay, the value of that line integral is 0. Okay, and finally, when it comes to the top side of the loop, we know that the value of the line integral is also 0 because the value of the field is 0, okay, for this entire upper region. So when we add up all of these contributions, okay, so that we get the line integral for the entire closed loop, okay, we find out that only the bottom side gives us a non-zero contribution. So the total value of the line integral is simply b times L. Next, we determine the total current passing through any surface bounded by that loop, okay, so that we can getting the right-hand side of Ampere's law. So we'll consider that for the rectangular loop, we'll consider the two-dimensional rectangular plane to be the surface bounded by that loop. And we note that this rectangular Amperian loop encloses a certain number of turns of wire. We'll call the number of turns enclosed by the loop big N. And the number of turns enclosed is simply equal to little n, that is the number of turns per unit length, times the total length. Okay, since each turn carries a current I, the total current enclosed by that loop then will be, okay, the number of turns enclosed by the loop, which is little n times L, times, okay, the current through any given loop. Okay, we're now ready to apply Ampere's law and equate the line integral with the encircled current. Okay, and when we do that, we equate these expressions here, okay, and solve for the resulting field. We see that the field for the region in the interior of the solenoid takes on a very simple form. Okay, the field has a value of mu naught, okay, that permeability constant, times the number of turns per unit length, little n, times the current. It's important to note here that a long solenoid is the magnetic equivalent of the parallel plate capacitor. since each device produces a uniform field in the interior of the device. That is, if the fringing effects at the edges can be ignored. So remember that the parallel plate capacitor effectively produces a uniform electric field in the interior region, whereas now we're seeing that, okay, a long solenoid produces a uniform magnetic field in the interior region of the device. As we stated previously, the solenoid, with its unique ability to produce a strong and uniform magnetic field, becomes a commonly used device in our modern-day technological world. So let's spend a few minutes investigating how solenoids are used in technology, starting with perhaps their most common use in the device known as the electromagnet. An electromagnet is nothing more than a current-carrying solenoid. Oftentimes, a ferromagnetic bar, usually made of iron, is inserted inside of the solenoid coil in order to concentrate and strengthen the magnetic field. So, what sort of factors affect the strength of the electromagnet's magnetic field? Well, using the expression we just derived for the magnetic field inside of the solenoid, two of these factors become obvious. The first is electric current. So, looking at the form of the field inside the solenoid, we see that there's a direct relationship between field strength and current. In other words, doubling the current will double the field strength. The second factor is the number of turns in the solenoid coil. Once again, using the relationship just derived, we see that there's also a direct relationship. As the number of turns increases, the field strength increases linearly. This is how you can develop very, very powerful electromagnets, because what this tells us is that, doubling the number of turns doubles the magnetic field strength. So with electromagnets consisting of solenoids with thousands of turns, you can develop very, very powerful magnetic fields inside those solenoids. The third factor has to do with the material core itself. Up to a certain point, the core will increase the strength of the magnetic field as the magnetic domains in the core are brought into alignment. So, in addition to the solenoid itself, which produces a strong magnetic field inside of it, putting a ferromagnetic material inside of there will further increase the strength of that magnetic field as you bring those magnetic domains into alignment. It turns out, though, that the most powerful electromagnets don't have iron cores, but rather use superconducting coils through which large electrical currents exist with virtually no resistance. So let's take a look at some common applications of electromagnets in technology, starting with perhaps the most simple application, that of the doorbell. So what you see here in this very simple schematic of the doorbell, that when the button is pushed, the circuit is complete and the electromagnet switches on and pulls the metal clapper assembly towards the bell. When the clapper assembly is in the position shown, it's making contact with the contact screw and the circuit is complete, as I'm showing you here in red. But as the clapper assembly is moving towards the bell, it no longer makes contact with the contact screw and the circuit is broken. When the circuit is broken, the electromagnet shuts off and the spring pulls the clapper assembly back towards the contact screw, allowing the cycle to repeat. So here we have a doorbell, which is a nice application to see electromagnets in action. You'll notice here with the doorbell we've got our two electromagnets. Of course we have the bell and we have our clapper assembly. Now if we take a look at how the doorbell works, you'll notice that when the button is pushed, the circuit is completed
and these electromagnets get turned on. When they get turned on, they pull the clapper, they attract the clapper to them. The clapper comes up and hits the bell. But now you'll notice the function of this contact screw here. When those electromagnets pull the clapper up to hit the bell, the contact is broken between the contact screw and this rod right here. And you'll be able to see this broken contact when I activate it. You'll see a blue spark there. And the point of that contact screw is that once that contact is broken, the electromagnets now shut off and that clapper falls back to its rest position. Once it does that, contact is once again restored. The electromagnets turn on, pull the clapper up to hit the bell, contact is broken, clapper falls back, and this process repeats itself over and over again quite quickly, probably about 60 times a second.
Let's take a look at another application of electromagnets, a rather important one for us, and that is the loudspeaker. Whether you're talking about the headphones on an iPod or a rather permanent speaker, the technology is very similar. Let's take a look at how electromagnets can be used to create sound waves. The typical loudspeaker consists of a current-carrying coil that is wrapped around the base of a flexible paper cone. So remember that current-carrying coil, aka solenoid, is really an electromagnet, and if you look in the diagram you'll see that it's attached to the paper cone. The coil is allowed to slide freely over the pole of a magnet, and as the diagram suggests, this magnet is not a typical bar magnet. It has a rather interesting shape, and you'll see that the outer concentric circle, you're seeing half of it in the diagram, represents the south pole of the magnet, while the inner concentric circle, the one which the cone slides over, represents the north pole of the magnet. If you've ever picked up a speaker, you may notice how heavy it is, and the weight of that has to do with the weight of the magnet. When a current exists in the coil becomes an electromagnet with the north and south pole. For one direction of current in the coil and attached cone will be repelled by the permanent magnet, and it'll make it move upwards. And you can guess that when the current is in the opposite direction, the coil and attached cone will be attracted to the permanent magnet and will move downwards. As the cone moves, it pushes the air in contact with it, creating a sound wave. Now, the time-varying alternating current in the coil has a certain pattern to it, producing a time-varying force and a time-varying sound wave with the pattern. So the idea is that your current is not constant, but the current has a certain pattern which matches the pattern of the sound wave you're trying to create. This can be produced by a microphone. And the pattern of that current gets translated into a force pattern that makes the cone move up and down. And as that cone moves up and down, it creates a sound wave also with the same pattern.
So another application of electromagnets that we're all very familiar with is the loudspeaker, or just speaker. Now, if you've ever had a chance to pick up a speaker, perhaps a car stereo speaker or a home speaker, you'll notice that they feel quite heavy. And what makes a speaker heavy is a rather large permanent magnet which is attached to the base of the speaker. The permanent magnet is quite heavy. Now, if we look at the makeup of a speaker, we see that we have a specially shaped permanent magnet, okay, which has an electromagnet, okay, that is free to move in the magnetic field of the permanent magnet, and attached to that electromagnet is a paper cone. Let's take a look over here. I'll show you a simulation of the loudspeaker. Now, what you're looking at here is the shape of the permanent magnet. You'll notice that it really consists of two cylinders. That inner cylinder right here really represents the north pole of a magnet, whereas the outer cylinder, the larger cylinder, really is the south pole of the magnet. or vice versa. It doesn't matter. So we have this specially shaped magnet, and over one of the poles of the magnet, over that interior pole, what we do is we place our electromagnet, which is really nothing more than a coil of wire. Usually it's wrapped around a paper cylinder. Okay, here I'm going to use a slinky to represent the coil. I mean, it really is a coil. So here's the coil of wire placed over the pole, the north pole of that inner magnet. Now, you can imagine that when we put a current in our electromagnet here, in our slinky, it becomes a magnet with a north and south pole. For one direction of the current, okay, the electromagnet will be repelled by the permanent magnet and it'll move upwards. For current in the opposite direction, the electromagnet will be attracted to the permanent magnet and it will move downwards. So you can see that by varying the direction of the current, we can make this electromagnet move up and down. And if we attach a paper cone to this electromagnet, as the electromagnet moves up and down, it will then push the air and create a sound wave or pressure wave. Now, a time-varying current can have a pattern to it. Maybe the pattern of that time-varying current matches your favorite song. So we can make this electromagnet move down in accordance with that pattern and cause the air to move in a very periodic way that also matches the pattern to recreate the sound wave. So let me take you over here and we'll show you a functioning loudspeaker. Now this one is a dissectable one, so we can see the parts a little better. You'll notice here at the base is the very large permanent magnet. Of course the inner pole is hidden, and if you can see through the plexiglass wall here, there's an electromagnet which is free to slide up and down in the magnetic field of the permanent magnet. Now I'm going to use this signal generator over here to provide an alternating current. Okay, and we'll increase the amplitude a bit, and you'll hear a high frequency sound here as that electromagnet is moving up and down. Now I haven't attached a paper cone here, but I have attached a wire loop, and we can check out the motion of the loop. Let's lower the frequency of this current here, this alternating current, and you'll be able to hear the sound wave create a change in pitch and frequency a little bit. Okay, and at a low enough frequency, you'll be able to see the motion of that wire loop. Okay, so right around here we can start to see that loop move. Okay, that loop begins to move as the electromagnet is moving up and down. Now this is at about 100 hertz, so this is still quite fast. If I bring it down to a low enough frequency so our eyes can actually detect the motion, okay, somewhere right about here, you will just about start to see that electromagnet, the individual up and down motions of it. Okay, and here it's creating a sound wave that's very low in frequency. It's very hard to hear. Okay, but you can see its effect on the wire loop. You can tell that electromagnet is moving up and down in the magnetic field of the permanent magnet. If I bring it down even lower, at some point you'll be able to see the electromagnet moving up and down. Now it's about 15 times a second. Your eye can easily see it move up and down. So you see here one more application of electromagnets, that of the loudspeaker.
So let's now take a look at perhaps the most important application of electromagnets in technology, and that is the electric motor. There are many different types of electric motors, but we will take a look at a very simple example of one and take a look at how it works. So all motors consist of a coil of wire, really an electromagnet, that is free to rotate in the fixed magnetic field of a permanent magnet. Now, I say permanent magnet. That permanent magnet could itself be another electromagnet, but in this schematic here, you see that There's an electromagnet on an armature which is free to spin, and it is brought near a permanent bar magnet. As you can see in the diagram, the north pole of the electromagnet would be repelled by the north pole of the permanent magnet. This would cause it to rotate half a turn. Once it rotates half a turn, you'd see that the south pole of the electromagnet would now be in contact with the north pole of the bar magnet, and it wouldn't want to rotate anymore. So now comes the reason that motors have a commutator. After rotating in a half circle, the commutator causes the current to change directions in the electromagnet, which then causes the polarity of the electromagnet to change as well. This allows the original south pole of the electromagnet to become a north pole, allowing the repulsion between the electromagnet and the permanent magnet to continue. So once again, the function of the commutator is to reverse the direction of the current, which then reverses the polarity of the electromagnet, which will allow it to now once again be repelled by the permanent magnet and continue to spin. You can take a second to pause the presentation and view the video clip of the electric motor.
So here, folks, we have an electric motor, which is a device used to convert electrical energy into mechanical energy. Now, there are many different types of motors. This is a St. Louis motor, but all motors have certain features in common. You'll notice here with this motor we have two permanent magnets which are surrounding an electromagnet which is attached to this armature so that it can spin freely. Also notice up here we have a metallic brush and a second metallic brush here which make contact with a split ring commutator here, and you'll see that split in the ring right here. So let's take a look at how a motor operates. What makes the armature of the motor turn is simply the repulsion of that electromagnet for the permanent magnet. Now you'll notice in this position the north pole of the electromagnet is repelled by the north pole of the permanent magnet, and similarly over here there's repulsion between these south poles. That causes the electromagnet to want to spin. But after it spins, you'll see that the north pole, which starts out over here, if it spins half a rotation, it would now be attracted to the south pole of the permanent magnet over here, in which case the motor would no longer want to spin. It would spin half a turn and stop. That is the function of the split ring commutator here. The split ring commutator causes the current in the electromagnet to change directions, which causes the polarity of the electromagnet to change directions after half a turn. So what starts out as a north pole over here, half a turn later becomes a south pole. And we see that once again in this position, the south pole of the electromagnet is repelled by the south pole of the permanent magnet. Likewise for the north poles, this causes the electromagnet to spin another half turn. And this process repeats. Let's turn on our electric motor and see it in action. Once again, we see this conversion of electrical energy provided by our power supply into mechanical energy, or the kinetic energy of the motor armature.
So another very common application of solenoids is the iron plunger. So the iron plunger, it operates, or it exploits the fact that the magnetic field of a solenoid is not uniform at the ends of the solenoid. There's this fringing effect, which has the effect of being able to draw a ferromagnetic material like an iron rod, to draw it right into the coil. Okay, so this effect will be demonstrated for you either in real time or in a video clip that will be inserted. So let's take a look at a few examples where we see this technology commonly used. The first being in solenoid valves to control fluid flows. So as you see here in the schematic, okay, we have the iron plunger here, which when the solenoid is not activated, it's in a closed position, preventing fluid flow. But once that solenoid gets activated, that iron plunger gets drawn up, and it opens the valve and allows the fluid to flow. Okay, this very simple technology is used in dishwashers and washing machines and automatic sprinkler systems to control the flow of water. Another very common application of this iron plunger is in the relay in the starter solenoid of most automobiles. So a starter solenoid, or sometimes called a starter relay, is that part of the automobile which will switch or relay a large electric current to the starter motor in response to a very small control current in the ignition circuit, and which in turn sets the engine in motion. So in a way, the starter relay or the starter solenoid functions very similar to a transistor in that it amplifies the power output. It can effectively switch a low current in the ignition system into a high current in the starter motor by using an electromagnetic solenoid rather than a semiconductor to perform the switching. So if we take a look at the schematic shown here, we see that when the ignition is switched on, it activates the solenoid over here, draws the iron plunger into the solenoid, and the first effect is that this contact over here, when the contact is made, we now have switched a low current in the ignition system to a large current which is needed to activate or run the starter motor. So that's the first effect. The second effect is that when that iron plunger is drawn in, the gear in the starter motor over here now moves into position here with a flywheel so that your starter motor can now cause the turning of your engine. The end result is that a very small current in the ignition system is used to trigger a large current in the starter motor. So you may have noticed at some point that if the starter solenoid receives insufficient power from the battery, you might end up with this clicking sound in your car, this very rapid clicking sound. So if that battery, if the starter motor, that solenoid doesn't receive sufficient power from the battery for whatever reason, because the battery's bad or because you've got a bad contact, the end result is that the solenoid doesn't fully draw that iron plunger into position so that the gear on the starter motor is not able to actually get into the correct position on the flywheel. And you hear a rapid clicking sound as it's not actually allowed to fully engage the flywheel and get in position. So the very last application of solenoids we'll take a look at is their use in medicine in the form of MRI scanners. Now, if any of you have ever had an MRI performed, you'll know that you get placed in this rather large tube and you're asked to hold relatively still. Well, although you can't see it, this large tube is really nothing more than a very powerful solenoid. Very often using superconducting coils to produce a very intense magnetic field. Now, it turns out that the protons in your cells behave like very tiny magnets, and they become aligned with this very intense external magnetic field of the solenoid. short bursts of radio waves aimed at the body will knock these protons out of alignment. And if you've ever had an MRI, you hear this, it's quite loud. You hear these short bursts of radio waves being produced, and they make a rather loud sound. When the radio waves are turned off, the protons will naturally realign with that external magnetic field of the solenoid, and in so doing, they will send out or create radio waves which can be picked up by receivers. So these radio waves form the image, okay, the scan. It turns out that protons in different tissues will realign at different rates, and thus sending out distinct signals, okay, which will allow an image to form. So you can imagine that if you're looking at protons in, let's say, a malignant tumor, okay, that those protons will align at different rates, will send out signals of different frequencies, okay, which will look distinctly different, let's say, from the protons of healthy cells. So in this way, it's the difference in the realignment rates that will form these distinct signals that we see as the scan. Alright, so now that we've examined the magnetic field of a solenoid and even took the extra step to look at applications of solenoids in modern technology, we'll turn our attention from solenoids to toroids. As the picture in the upper right-hand portion of the slide indicates, a toroid is really nothing more than a solenoid that has been bent into a circular shape, resembling that of a donut. So, in this problem, we're asked to find the magnetic field of a solenoid having n turns, and this particular solenoid, we're told, is used in a fusion reactor. So the first step in applying Ampere's law will be quite easy, since we already know the magnetic field configuration of the solenoid. Since the magnetic field lines inside the straight solenoid were parallel to the solenoid axis, when the solenoid gets bent into a circle, we would expect the field lines inside the solenoid to change from straight lines to circles. So the choice of an Amperian loop then becomes obvious, because if the magnetic field lines are circular, we'll choose an Amperian loop to match that symmetry. So we want to choose a circular Amperian loop, and by doing so, the magnetic field will be constant in magnitude over the entire integration path. So we'll draw in an appropriate Amperian loop. Notice that a toroid has both an inner radius and an outer radius. So we want to be careful that when we draw in that Amperian loop, okay, so that it is passing through a field point inside of the toroid, okay, we want to make sure that that radius is somewhere in between the inner radius and outer radius. Alright, so we are now in a position to determine the magnetic field direction along the integration path, and using the right-hand current rule, you see that the current in the inner coils is coming out of the plane of the paper. So placing the thumb of our right hand in the direction of that current, we see that our fingers naturally curl in a counterclockwise direction. So the field inside of that toroid is going to be in a counterclockwise direction. So we will choose to traverse the loop in the same direction as the field. Note that both the field and the infinitesimal displacement vector ds are parallel to one another, as we see this over and over again with this particular symmetry. In which case, when we evaluate that line integral around the closed integration path, since the argument of the cosine function is 0, and since the magnetic field is constant over the entire integration path, it can be taken outside of the integral. So as we've seen many times before, the integral of ds is simply the circumference of that circular integration path, 2 pi r. Determining the current passing through any surface bounded by that Amperian loop, if we look at a circular plane, okay, of radius r, we see that the number of turns of the number of coils, the number of turns is capital N, and we see that each of those turns has current which would penetrate that surface. So the total current penetrating that two-dimensional circular plane would then be the number of turn times the current through any single turn. And finally, applying Ampere's law, equating left-hand side with right-hand side, okay, we can solve for the magnetic field, and we get the following expression, that the field inside that toroid, okay, is equal to, okay, mu naught, the permeability constant, times the number of turn times the current divided by the factor 2 pi r. So the question asks here, why would toroidal coils be used in fusion reactors? Well, remember, one of the issues with fusion is that the very, very high temperatures required to get hydrogen nuclei to fuse together to form heavier elements, those very, very high temperatures can have the effect of, sort of melting the containment vessel. But you can imagine that using a toroidal coil, okay, since those charged particles in the plasma state become trapped in the magnetic field lines, no physical containment vessel would really be necessary to contain the plasma. Simply having a very powerful magnetic field in the form of that toroid would allow the particles to move in the direction of the field without actually making contact with the vessel walls. So in this very last example of applying Ampere's law, we'll take a look at the magnetic field of a current sheet. So we've looked at the magnetic field that forms around a current carrying wire where that current is confined to a right circular cylinder. What happens here where we look at current, a uniform current traveling through a planar sheet? We'll assume that the sheet is infinite in dimension and that the current is distributed uniformly along the sheet with a current density given by J naught. That is a current per unit width. We're asked to find the magnetic field for the sheet at an arbitrary point outside of the sheet. So as always, we start by identifying the symmetry of the current distribution, okay, which will allow us to determine the pattern of the magnetic field lines. We see here that the planar symmetry of that current distribution suggests that the field lines must be parallel to the plane itself. In order for the field lines to encircle their source, however, the field lines above the sheet must be opposite in direction to those below the sheet. Now, using the right-hand current rule, that is placing the thumb of your right hand in the direction of the current, we see that below the sheet, the field lines will point to the right, whereas above the sheet, the field lines must point to the left. So the choice of the Amperian loop should be obvious in this case, such that the magnetic field will be constant in magnitude over the integration path. So choosing a rectangular Amperian loop, let's say of width W, will allow the magnetic field to be constant in magnitude and direction along each 4 segments of that loop. So we will draw an appropriate Amperian loop so that it passes through an arbitrary field point outside of the planar sheet. Okay, so here is our blue Amperian loop that we have drawn. So the next step should be quite easy because we see the form of the magnetic field, we see the integration path there. We note that the magnetic field and the infinitesimal displacement vector ds are either parallel to each other or perpendicular to each other for each of the 4 segments of our rectangular Amperian loop. So we will choose to traverse the loop in the counterclockwise direction, starting at the upper left-hand corner. So we notice that for both the left-hand side of our loop and the right-hand side of the loop, the magnetic field is perpendicular to ds, in which case the value of the line integral becomes 0. For the top portion of the loop and the bottom portion of the loop, we note that B and ds are in the same direction. They're parallel to each other, so we are taking the cosine of 0, okay, for both top and bottom. Since the magnetic field is constant there, it can be taken out of the integral sign, and once again the integral of ds is just the length of, okay, or I should say the width of the rectangle W. So at the end of the day, when we evaluate the entire line integral around that closed integration path, okay, summing up our results for each of those 4 segments, we end up with twice the field strength times W, the width of the loop. In determining the total current passing through any surface bounded by the loop, okay, the encircled current is simply going to be the current density, which remember is the current per unit width, times the width of that loop, W. That's going to give us an expression for the total current which is enclosed or which penetrates, okay, the rectangular surface bounded by that loop. So finally, applying Ampere's law and setting the line integral equal to mu naught times I, we can solve for the field, and we end up with the expression as follows, that the field takes on this very simple form, 1/2, okay, the permeability constant mu naught times the current density J naught. Now we see here that the field is certainly constant, okay, everywhere. A very interesting result, that the magnitude of the field has a constant value at any point outside of that current distribution. So now that we've looked at the form of the magnetic field surrounding various current distributions, let's take a look back and at various charge distributions that produced electric fields, and look at some of the similarities between the field strength and distance for both electric fields and magnetic fields. Now, you may recall that when we looked at the charge distribution of the electric dipole, we saw that the electric field had a 1/r³ dependence. When we look at the magnetic dipole, which is a small current loop, we see the same sort of field dependence and the same sort of shape to the field. Now, in the next row here in the matrix, we see how charge distributions differ from current distributions. In other words, a point charge or a spherically symmetric charge distribution, the electric field had a 1/r² dependence. There is no such analog for current distributions. Okay, it is not possible for any kind of steady state current to give you a 1/r² dependence. And recall that we said while there's such thing as an individual point charge, there is no such thing as a magnetic monopole. Now, when we look at a charge distribution that had line symmetry, okay, we saw that the field got weaker as 1/r. There was a 1/r dependence, okay, with distance. We also see that a current distribution with line symmetry, that is for a wire, there's also this 1/r dependence between the field strength and distance. And finally, as we see in the last example, for the infinite flat sheet of charge, it has a lot in common with the current sheet. Okay, that for the infinite flat sheet of charge, we ended up with an electric field that was constant, okay, regardless of how far the field point was away from the sheet. In other words, there was no dependence on distance. And as we just saw in the last example, we saw the same holds true for the infinite current sheet.